This lecture is on conformations and their applications. Part 1. What are conformations? Conformations are different, temporary 3D arrangements of atoms in a molecule due to free rotation around single bonds. Because they're temporary, you can't put different conformations, also called conformers, in different bottles. They're all the same compound. For example, you can rotate freely around the carbon-carbon bond in ethane. That gives you an infinite number of different conformers. Looking down the CC bond, you can draw the bonds on the front carbon in front of an imaginary circle, and the bonds on the back carbon poke out behind the circle. This is called a Newman projection. The first structure that you see is a sawhorse projection. That's the one where the carbon-carbon bond is shown horizontally. Let's take a closer look at these ethane conformers. In ethane, when the angle between the front and back CH bonds, which is the dihedral angle, is 60 degrees, there is no bond repulsion, which is known as torsional strain. This is the most stable or lowest energy staggered conformer. If you rotate to 120 degrees, when the dihedral angle is 0 degrees, there's a maximum torsional strain due to the close proximity of the bonds, and this is the eclipsed conformer. Below, you'll see that there's an animation showing the potential energies of the different conformers as the front portion of the ethane molecule rotates in a Newman projection. Let's take a look at butane conformers. Here is the lowest potential energy conformer of butane at 0 kcal per mole, called anti. On the left is its sawhorse projection, and on the right is its Newman projection. The large methyl groups are 180 degrees from each other, so there's no torsional strain, that is bond overlap, or steric strain, which is collision between atoms. Now, if we rotate 60 degrees, the potential energy increases to 3.8 kcal per mole for the eclipsed 1 conformer shown below. There's torsional strain because of bond overlap, and the large methyl groups are 0 degrees from hydrogen atoms, which is close enough to collide with them. This creates steric strain, collision between atoms. Steric strain occurs when one group larger than hydrogen collides with another atom or group. For a hydrogen atom, the dihedral angle needs to be 0 degrees for collision with a larger atom or group. Rotate 120 degrees, and the potential energy drops to 0.9 kcal per mole for the gauche conformer shown below. Now the torsional strain is gone. There is no longer any bond overlap. The large methyl groups are 60 degrees from each other, close enough to barely collide, just touch, and that's slight steric strain. Rotate 180 degrees to get the highest potential energy conformer of butane at a whopping 4.5 kcal per mole, called eclipse 2, and that's shown below. There is both torsional strain, because there is a 0 degree dihedral angle, causing maximum bond repulsion, and maximum steric strain, because the large methyl groups collide with each other. The following animation shows the rotation of the butane molecule around the C2-C3 axis, which are the two carbons in the middle of the butane carbon chain. This creates the conformers previously discussed and shows their potential energy. Note that after 180 degree rotation, the pattern repeats. Practice problem 1. Sighting down the indicated bond, draw the original conformer and the most stable conformer of the following compound as Newman projections. Justify your drawing of the most stable conformer. Now, let's review. We have two kinds of energy we have to worry about. Torsional strain, where you have a 0-degree dihedral angle due to bond overlap, and steric strain, caused by collision between atoms. So those are the two kinds of energy you want to minimize when you want to draw the most stable conformer. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 1. With the original conformer, if you sight down the carbon-carbon bond, you'll see that the benzene ring, shown in red, is in the top portion of the molecule, and the methyl group in the front is in the bottom left corner, and the hydrogen in the front is in the bottom right corner. In the back, we have a methyl group, which is in the upper right, a hydrogen atom, which is in the upper left, and another hydrogen atom, which is straight down. This gives us a gauche interaction between the benzene ring or phenyl group and a methyl group. This is steric strain caused by phenyl-methyl repulsion at 60-degree dihedral angle. Now, a benzene ring's pretty big, so let's see if we can minimize the steric repulsion by rotating it away and get our lowest energy conformer. Now we still have a gauche interaction, but there's less steric strain from methyl-methyl repulsion than the original phenyl-methyl repulsion, because methyl is smaller than phenyl. The E2 reaction, an application of conformations. Consider the following reaction. We have ETO-, where ET is CH3CH2 or ethyl, and that whole thing is known as ethoxide. That's pulling off a proton, which is shown in red and circled, to form ethanol. You also obtain an alkene and a species L-. So what is that? L is a leaving group. It can be chloride, bromide, iodide, or sulfonate, which is OSO2R. These are all leaving groups because they are the conjugate bases of strong acids and are easily displaced from the molecule. You can replace ethoxide with other strong bases. What are these? Well, they could be hydroxide, OH-, or anything with a negatively charged oxygen connected to an sp3 hybridized carbon. The rate of this reaction is equal to a rate constant K times the concentration of the compound with the leaving group raised to the first power times the concentration of the base raised to the first power. Thus, the overall order of this reaction is second order. We call it an elimination reaction because we have knocked pieces off the molecule or eliminated them from the molecule. And as a second order elimination, we designate it E2. Now, it may seem surprising that in this E2 reaction, you see those bulky benzene rings on the same side of the alkene. They're cis to each other, which create a lot of steric strain. How come the benzene rings can't be trans to each other? So we need a mechanism to explain why only one alkene formed and to fit the second order rate law. And that mechanism is shown below. The ethoxide pulls off the proton at the same time that the carbon-hydrogen bond breaks. You form a carbon-carbon pi bond, and you displace the leaving group. For a flexible molecule like the one above, for E2, the alpha carbon to leaving group bond and the beta CH bond must be anti-paraplanar. That means they must be 180 degrees apart and in the same plane. Here is the Newman projection for the E2 mechanism. It's a concerted mechanism, which means that the bond breaking and bond forming events all occur in one step. The ethoxide pulls off the proton, and simultaneously the electrons flow toward the carbon that has the leaving group attached and the leaving group is displaced, and the pi bond forms. Note that you can easily see in the Newman projection that the beta hydrogen and the alpha leaving group are 180 degrees across, or anti. They're also occupying the same plane, so that's anti-paraplanar. If we try to get the benzene rings to be as far away from each other as possible, then if we rotate them into a position in which the leaving group and the beta hydrogen will now be 60 degrees from each other. That doesn't work. That's not anti-paraplanar, and thus it's not allowed for an E2 reaction. The question is, why? Well, we have to look more carefully at the nature of the sigma bond. There are two types of overlap that is direct between atoms. Okay, one is a bond-forming overlap, which we call a sigma bond, and the other is one in which there's repulsion between those overlapping orbitals, and that's called antibonding sigma, sigma star. The sigma bond is a filled orbital. There are 2 electrons in it. The antibonding sigma is an empty orbital because it's high energy. You don't want to put electrons in there. So in the mechanism of the E2 reaction, when ethoxide removes the proton, if the electrons from the sigma bond of CH are able to fill in the antibonding sigma bond of Cl, that will cause destruction of the carbon leaving group sigma bond. It will make it break. It's because the energy of the antibonding sigma, being high energy, will counteract the low energy sigma bond of C to L, causing the Cl bond to break. Then the new bond will form a pi bond between what was a sigma bond and an antibonding sigma bond. Note that the overlap of the CH sigma bond with the antibonding sigma bond of Cl is exactly what you need for a pi bond. See how the orbitals are placed parallel to each other? And that's why anti-paraplanar arrangement of the alpha Cl bond and the beta CH bond lead to an effective E2 reaction, whereas any other kind of dihedral angle doesn't work because the overlap isn't appropriate. Practice problem 2. Using the anti-paraplanar rule and Newman projection, draw the mechanism and predict the product or products of each of the following E2 reactions. Be sure to look for the leaving group, which would be chlorine, bromine, iodine, or sulfonate, and that's the alpha carbon leaving group bond. And adjacent to that, you need a beta CH bond in order for you to get an E2 reaction. Make sure that the alpha Cl bond and the beta CH bond are anti-paraplanar, and if they're not, rotate them so that they are before you try to write the mechanism and predict the product of the E2 reaction. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 2. In part A, the alpha carbon to leaving group bond, in this case the leaving group is bromine, and the beta CH bond are already anti-paraplanar in the Sawhorse projection. So ethoxide can, in a concerted manner, remove the beta hydrogen, electrons flow toward the alpha carbon and displace the leaving group. In the Newman projection, you can also see how the beta CH bond and the alpha CBr bond are anti-paraplanar. Note that the benzene ring and the tert-butyl group are gauche to each other, they're 60 degrees apart. That means that in the product they're going to be cis, and that's what we see in the drawing to the right. The tert-butyl group on one carbon and the phenyl group, the benzene ring, on the other carbon are cis to each other. If you look at the Newman projection again, note that the red methyl group and the tert-butyl group are anti to each other. Okay, So since they're anti, that means that they're going to be trans to each other. And that's exactly what we see in the product. In part B, the alpha CBr bond and the beta CH bond are not originally anti-paraplanar in the sawhorse projection. So what we have to do, using our Newman projection, is to rotate those two groups so that they are anti-paraplanar. Once we get that geometry, note that the tert-butyl group and the benzene ring are now across from each other, so they're going to be trans in the final product. And that's what we see. So in order to get the correct geometry in our alkene, you have to first make sure that your leaving group and your beta CH bond are antiparaplanar. Notice that sometimes I pronounce ANTI anti and sometimes anti, and it's okay if you flip back and forth. In part C, the alpha CBr bond and the beta CH bond are already antiparaplanar, and so in both the sawhorse and the Newman projection, we see that we can get our final product, which is showing the tert-butyl group and the benzene ring cis to each other. But we can also use the other hydrogen, that's beta, rotate that hydrogen in position so that it is anti-paraplanar to the bromine. This puts the tert-butyl group and the benzene ring across from each other, and thus trans in the final product. So in part C, we actually have two possible alkene products, one which is cis and the other which is trans. In practice, unless we have a really bulky base, if there is more than one E2 product possible, the major product will be the most substituted and most stable alkene. In this case, the trans product, because this gives us the least amount of steric strain, and the alkene is disubstituted.